Hello friends, welcome back to my classroom. In this class, I'll try to explain joint probability distribution, marginal distributions and stochastical independence of variables. Suppose x is a random variable that takes the values say 1, 2 and 3. So we have already discussed about the probability distribution of say this single random variable in my first lecture of this playlist, and if you want to revisit you can check the link in the description box. And along with this x, suppose there is one more random variable y, say y is taking the values 2, 4 and 6. And if we are interested in the probability that x is taking a particular value say 3 and y is taking a particular value say 4, okay, if we are interested in probability that x is 3 and y is 4, so this is called as joint probability. Okay, so here we are not talking about what is the probability that x is 3, or we are not talking about what is the probability that y is 4, but we are talking about the probability that x is 3 and also y is 4. Okay, so what is the probability that x will be 3 and y will be 4? Okay, so these joint probabilities for different values of x and different values of y is represented in a table called contingency table. Okay, so this contingency table represents the probabilities for different values of x and different values of y. So the probability that x takes the value x1 and y takes the value y1 is denoted by p11. So x takes the value 1 and y takes the value y1 is represented by p11. Okay, you can check this p11. It's written in the first row, first column. First row is for x1 and first column is for y1. Similarly, what is p32? So p32 is probability that x is taking the value x3 and y is taking the value y2. Okay, and what is the notation for probability that x is equal to x2 and y is equal to y1? It's going to be p21. Okay, so for all the combinations we find the probabilities pij and we represent it in the table. Okay, and one more thing you need to note that sum of all these probabilities, so if you add all these probabilities, p11 plus p12 plus p13 plus p21 plus p22 p23 plus p31 plus p32 plus p33, this sum should be equal to 1. So sum of all these probabilities is 1. Okay, unless summation of this pij is 1, it is not a valid probability distribution. And let us take an example. Suppose a shop owner wants to understand about his ice cream sales on different weather conditions. He has to consider two variables. One is for weather and other is for sales. So suppose x is taking the values x1, x2, x3 and y is taking the values y1, y2, y3, where x1 is represents sunny day, x2 represents cloudy day and x3 rainy, and y1 high sale of ice creams, y2 is medium sale of ice creams and y3 is low sale of ice cream. So what does this 0.15 represent? 0.15 is the probability that x is taking the value x2 and y is taking the value y1. That means what is the probability that on a cloudy day the ice cream sale is high? Okay, the probability that the ice cream sale will be high on a cloudy day is 0.15. So similarly, this 0.05 is on a sunny day, the probability that there will be a low sale. Okay, So these are the different values on different weather conditions. And how does this help the shop owner? He can understand the effect of weather conditions on sales of ice cream, and he can make better decisions. Like on sunny days, he can increase the stock, because on sunny days there is a high probability that high sales will happen. Okay, and on rainy days, definitely high sales will be less, the probability will be less, and he can offer discounts. Okay, he can make his own plans for his business. Let us understand what is marginal distribution. Okay, what is a marginal distribution? It is the probability of a single random variable from a joint probability distribution. That means, suppose we have a joint probability distribution on two variables, x and y. Now if we want to consider a single variable from this, okay, and not considering the other variable. So if we are interested in finding what is the probability that x takes the values and not depending on y values. So what is the probability that x takes the value x1, x takes the value x2, and x takes the value x3. So if we are interested in only the variable x, this is called as marginal distribution of x. Okay. Similarly, if we are interested in finding the probability distribution of y, okay, ignoring the x values, okay, whatever may be the values of x, whatever may be the probabilities that x takes a particular value, okay, we are just interested in finding the probability that y having a particular value. Okay, so these are called marginal, this is called the marginal distribution of y. So marginal distribution of x is usually denoted by, the probabilities are denoted by p1, p2, and p3, and for y it is denoted by q1, q2, and q3. Okay, these are also probabilities only. So uh, 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 just to make the difference between x and y, in x usually we denote the probabilities by p's, and in y we denote the probabilities by using q's. Right? So how to find these probabilities? Like we want to find what is the probability that x takes the value x1. So we are just ignoring about the y taking the values, different values. So we just have to add the corresponding row of x taking the value x1. So that sum, whatever sum of that row, that will be the probability that x having the value x1. Okay. Similarly, for x taking the value x2, you can add the second row, all the values in the second row, and for x having the value x3, you can add all the values of third row. Okay. Similarly, for y, you can consider the columns, first column, second column, and third column. So let's understand this by taking an example. Okay, take this problem as the example for finding the marginal distribution. Find the marginal distributions of x and y for the below joint probability distribution. So in the joint probability distribution, all the probabilities are known, like just to have an understanding, a better understanding. So probability that x is taking the value 5 and y is taking the value 3 is given by 0.15. That means P23 is second row, first column. P21 is 0.15. So this is the joint probability distribution given. But the question is to separate them, separate x and y. I want to have marginal distribution of x. So here x is taking two values, 2 and 5. 2 is first value and 5 is second value. So I need to find the probabilities. The first value is 2. What is the probability that x is 2? X is equal to 2. So how do I get this? I don't look at what's happening with y. I just have to take the row where x is 2, and we need to add all these probabilities. So what are these probabilities? 0.2 plus 0.1 plus 0.3. So 3, 2, 1, 0.6. So the probability that x is equal to 2 will be 0.6. And similarly, the probability that x is equal to 5 is 0.15 plus 0.05 plus 0.2. So this sum will be equal to 0.2, 0.5, 0.2. So this way is going to be 0.4. So very simple. You just have to add all the values in the first row for the first value of x, and sum of all the values in the second row for the second value of x. So this is how we get the marginal distribution of x. And similarly, for marginal distribution of y is taking the values 3, 8 and 10. So 3, 8 and 10. Here we do not consider the values of x. We just concentrate on the probability that y takes the value 3, 8 and 10. So what is the probability that y takes the value 3? 3 is given in the first column. So you can observe in the table first column. So what are the probability that y takes the value 3, or first probability is 0.2 and plus second probability is 0.15. So totally it is 0.35. So probability that y is equal to 3 is 0.35. Similarly, for y is equal to 8, we need to consider the second column. Second column has the values 0.10 and 0.05. So if you add them, you will have 0.15. And for the third value of y is equal to 10. The probability that y is equal to 10 is the sum of all the probabilities in the third column. Third column, if you add 0.3 plus 0.2, 0.5. So this is called marginal distribution of y. Okay. Hope you have understood about joint probability distribution and how to calculate marginal distributions from the joint probability distribution. Okay. So now let's understand what is the definition of stochastical independencies. Two random variables x and y are said to be stochastically independent if the occurrence of one does not affect the probability of occurrence of the other. That means x doesn't depend on y and y values doesn't depend on x. Very simple. So one more example, let's take one student A, the probability that he gets A plus in the exam, B in the exam and C in the exam. Maybe probability 0.3, 0.2 and 0.1. And one more student is there, B. The probability that he takes the grades A plus, B and C may be 0.5, 0.3. Okay, sorry, 0.32. Maybe this is 0.5 because total should be 1. 0.5, 0.3 and 0.2. So here you can observe that these are completely independent. The probability that A scores well or not, it doesn't affect the probability of B. You can have the joint probability distribution here, like what is the probability that A and B both will get A plus, or what is the probability that A gets C grade and B gets A plus. All right, like this joint probabilities you may have, but they don't depend on each other. Okay, so they are stochastically independent random variables. Okay, so knowing the value of one variable gives no information about the other. So then we say they are stochastically independent. So how do you check whether whether the variables, given variables, are stochastically independent or not? So that is checked mathematically by uh, checking this equation Pij is equal to Pi into Qj, whether it's true for all Ij. So you in the I mean already I have explained what is P1, P2, P3 is like x1, x2, x3. These are the probabilities that x is taking the value x1 is P1, x2 is P2, x3 is P3. And similarly you may have the probabilities P of y taking the value y1, y2, y3, and with the probabilities q1, q2 and q3. Okay, suppose these are the marginal distributions, marginal distribution of x, and this is marginal distribution of y. And also we have a joint probability distribution. Let's say x, y is taking the values y1, y2, y3, and x is taking the value x1, x2, x3. So these are probabilities are P11, P12, P13. Next row it will be P21, P22, P23, and next row it is P31, P32 and P33. Okay. So this green table is the joint probability distribution, and this blue tables are marginal distribution of x and marginal distribution of y. Now to check whether x and y are stochastically independent or not, we need to check whether Pij is same as Pi multiplied by Qj. So that means we need to check whether P11, okay, what I am encircling, P11, is it same as P1 in the marginal distribution of x multiplied by Q1 in the marginal distribution of y. So P11, whether it is equal to P1 multiplied by Q1. Okay, question is, are they equal? And similarly, P3 multiplied by Q2, is this equal to P3? P3 in the marginal distribution of x, P3, and Q2 is in the marginal distribution of y. If I multiply P3 and Q2, will it be equal to P32 in the contingency table of joint probability distribution? So not just for these two values, it should be true for all the values, okay, of the contingency table, all the combinations. All right, Pij should be equal to Pi multiplied by Qj. All right, if they are equal for all I and j's, then we can conclude that the random variables x and y are stochastically independent. Okay, so let us take a couple of examples. Show that the random variable x and y with the joint probability distribution represented by following contingency table are stochastically independent or not. So what is P11 here? 0.06. P12 is 0.15. P13 is 0.09. This is P21, this is P22, and this is P23. So to check whether they are stochastically independent or not, first we need the marginal distributions of x and y. So let us find the marginal distribution of x first. So 2 and 5 are the values x is taking, and marginal distribution of y is taking the values 3, 8 and 10. Okay, so what are the corresponding probabilities? P of x, P of x, first value of x is 2. X is 2 means 0. In the row, first row, 0.06 plus 0.15 plus 0.09. So this sum is going to be 15.3, 0.3. So this will be 0.3. And what is the probability that x equal to 5? X equal to 5 is 0.14 plus 0.35 plus 0.21. Sum of all the values in the second row. So this is going to be 0.7. So this is the marginal distribution of x. And for marginal distribution of y, let me do it in the contingency table itself. 0.06 plus 0.06 0.14. If I add the values in the first column, I'll get 0.2. And the sum of the values in the second column is 0.35 plus 0.15 is 0.5. And third column is 0.21 plus 0.09 is 0.3. So let me fill these values in the marginal distribution of y. 0.2, 0.5 and 0.3. So marginal distribution of x and y are ready. So let us now check what is stochastical, whether they are stochastically independent or not. So now what is P1 here? P1 is 0.3, P2 is 0.7. Similarly, Q1 is 0.2, Q2 is 0.5 and Q3 is 0.3. Let us check one by one values. First let me take P1 into Q1. P1 multiplied by Q1. What is P1? P1 is 0.3 and I am multiplying it with Q1. Q1 is 0.2. So you have to take the value, P1 value from X table and Q1 value from Y table. So if, oh sorry, I made a mistake. This is not 0.5, this should be 0.2. So if I multiply these two values, 3 2s are 6. So 0.2 decimal points are there. So this is 0.06. Now the question is this 0.06 same as P11? So this P11 will be available in the contingency table. So look at the contingency table of joint probability distribution. So 0.06 P11 value is same as the value what is there in the contingency table. It is equal to P11, 0.06. Similarly, let us take the P1 itself, keep P1 but change the value of Q. So we need to check for all the combinations. So P1 multiplied by Q2. P1 is 0.3 and Q2 is 0.5. And if you multiply these two, 5 3s are 15.15. Is this P12? Yes. Let us check what is P12. P12 is, yes, it is 0.15. Okay. So similarly, you can check for other values. P1 multiplied by Q3, 0.3 multiplied by 0.3, which is 0.09. Yes, it is equal to P13. And now P1 with all Q's are done. Now I'll go with P2. P2 multiplied by Q1 is 0.7 multiplied by 0.2, 0.14. P2 multiplied by Q2 is 0.7 into 0.5 is 0.35 and P2 multiplied by Q3, 0.7 into 0.3. This is 0.21. Are they equal to corresponding Pij's? P2 into Q1 is 0.14. 0.14 is P21. Yes, P21 is 0.14. That we can check in the table. Similarly, 0.35 is P22. Okay, so this is P22 and P23 is 0.21. 0.21 is P23. Right? So Pij is same as Pi multiplied by Qj for all the values of I and j. Hence, we can conclude that x and y are stochastically independent. Okay. So for any joint probability distribution, it's very simple to check whether stochastically independent or not. We just need to get the marginal distributions of x and y and check Pi multiplied by Qj is Pij or not. Okay. And let's consider one more example just to show that all the joint probability distributions will not have stochastically independent random variables. Sometimes x and y depend on each other. Like this is a marginal joint probability distribution. So first let's find the marginal distributions of x. So marginal distribution of X is taking the values 2 and 5, and marginal distribution of Y is taking the values 3, 8 and 10. Okay, so probability of X, so 2. So if I add first row, I'll get 0.1 plus 0.2 plus 0.1, 0.4, and second row 0.3 plus 0.1, 0.4 plus 0.2, 0.6. Okay, and make sure this sum will also be 1. You just cross verify. It will be 1. If it is not 1, you have made some mistake in the calculation. You can cross check. Okay, you can correct it. And for Y, first column sum is 0.1 plus 0.3. That will be 0.4. And second column is 0.2 plus 0.1. This will be 0.3. And third column 0.2 plus 0.1. This is also 0.3. Now I need to check whether Pij is same as Pi multiplied by Qj. So let me take the first values, P1 multiplied by Q1. What is P1? 0.4. Okay, and Q1 is also 0.4. I will multiply 0.4 and 0.4, and I'll get 4 4s are 16, 0.16. And is this same as P11? So 0.16, no. P11 is actually 0.1, not 0.16. So 0.16 is not equal to P11. So since this is not, P1 into Q1 is not equal to P11. In the first calculation itself, we got to know that they are not stochastically independent. Okay, so even if for one Pi multiplied by Qj, if it fails to be Pij, then they cannot be stochastically independent. So since first value itself shows that they are stochastically independent, we can stop here and we can conclude that they are not stochastically independent. That means for to be stochastically independent, for all the values, Pij should be equal to Pi multiplied by Qj. Or even if for one value it fails, then they are not stochastically independent. Okay, so I hope you have understood the definition of joint probability distribution, and how to compute marginal distributions from a joint probability distribution, and how to check whether they are stochastically independent or not. And in the next class, let's discuss about mean and covariance of joint probability distribution. Okay, thank you.